Hello, I'm Jonathan Aldrich. Today, let's talk about pointers. Pointers serve two main purposes in modern languages. They provide efficient access to objects on the stack, as in C or in Rust. This can be safe if not carefully managed, because data that's on the stack will go away when a function returns. Rust has a type system that we'll look at later that enforces safety for this. The second main purpose is dynamic creation of linked data structures, in conjunction with the heap storage manager. This can also be safe if dangling pointers are dereferenced, and we'll see ways of dealing with that as well. One of the main approaches is garbage collection, but Rust has a static type system that again does the same thing. Many safe languages only allow the second case, pointers to heap data structures, because this is easier to check for safety, again using mechanisms like garbage collection. Some languages, such as Java, provide a higher level reference model, which really builds in pointers. We don't see the pointers explicitly in the type systems, but they're there under the hood. It turns out that we can model references with pointers, and so we'll cover them as part of this discussion. A useful distinction is to distinguish between pointers versus addresses. A pointer is an abstraction. It's basically a value that refers to an object. On the other hand, an address is a particular implementation. It's the location of a word in memory. Now, pointers are often implemented with addresses, but not always. For example, if you have a segmented machine, then a pointer might be a pair of a segment and an address. We'll see later on that we can make languages safe from dangling pointers by keeping track of a pointer as an address and then also an access key that helps to check for safety. Let's look at modeling pointers. We're going to choose to model pointers with three constructs. We'll start with a new operation, which is typical of C++ or Java. An equivalent might be malloc in C, but we'll type check it a little bit more as C++ does. We'll have a C-style dereference operation, star p, and we'll have C-style pointer assignments. In other words, star p gets E. The types we'll model include pointer types, T star. And we read this from right to left as in C. So T star means we have a pointer to some type T or tau in this case. In order to model execution, we'll track locations L on the heap. Imagine there's an infinite set of locations. We won't model them as integers in this case, but some abstract set of locations, and those will be our representation of pointers. Finally, we'll use a store, which we'll denote with the letter S, to represent the heap. The store maps locations to values that are stored in those locations. Finally, in our typing rules, we'll track the types of locations in a store typing that we'll use sigma for. The grammar at the bottom shows all these constructs added to the expressions, the values, the types, and the types of the language. What is the dynamic semantics of pointers? Well, we're going to introduce a new judgment form in order to do this. The new judgment form is required in order to track changes to the heap that happen when we assign to a pointer. So our new judgment has the form S, E, turnstile E evaluates to S prime, V. What this means is, given some store, basically a representation of the heap S, and some environment that maps variables to values E, then evaluating the expression E yields some new store, S prime, right, which might have updates because we've assigned to locations in the store, and a new value, and a value V, which is what the expression evaluates to. Now we can write some new rules. Let's look at the rule for new. When we evaluate an expression new E, we're first going to evaluate E because that's going to be the initial value for this storage location. We evaluate E, we get a new store, store1 and value V. We're going to choose some new location that has not been allocated yet in the store. So the store, think of it as a finite mapping. It only contains the locations we've allocated yet. We're going to choose a new location from the infinite set of possible locations. And then that will be our location for this new cell in the memory. So we update our store, we take store S1 and we extend it with a mapping from L to this value that we initialized the store with. And then we have S2, and that will be the resulting store after we evaluate expression new E. The value that we get out of it is just the location that we allocated. This business about choosing a new location is implemented in the compiler with an allocator that might simply have a list of free locations and choose the next one off of the list. Once we have a pointer, we can dereference it. So *e is the syntax for that. We evaluate this by first evaluating the expression e, which gives us a location, L. Of course, there might be side effects in e, and so we might get a new store S1. We look in that new store S1 at the location L, and we get some value out. That is the eventual value of our dereference. Finally, we can assign into pointers. So *e1 gets e2. We'll evaluate both e1 and e2, getting a location for e1, where we're going to store the value, and getting a value for e2, which is the value we're going to store there. We then compute a heap S3, which will be the resulting heap of our program. In this rule, we start with starting heap S0, and evaluating E1 might have side effects, so we get an updated heap S1. We use that heap to evaluate E2, that gives us an updated heap S2, and then S2 is the heap that we update where we set the mapping of L to be the new value V, replacing whatever was there before. Our assignment expression yields the new store S3 and also returns evaluates the value V, which was just the right-hand side of the assignment. This is a common semantics for languages that have assignment as expressions, including, for example, C. Because we have a new form of evaluation judgment, we have to update our existing rules to pass around the store. This happens in a relatively straightforward way, following the pattern that I already set for the assignment rule in the previous slide. So for example, if we look at E1 op E2, where we might have an operator like plus, we'll first evaluate E1, we'll change the store from S0 to S1, we'll use that new store S1 to evaluate E2, getting some store S2, and then we'll do our binary computation and return S2. So the store is basically a mathematical construct that gets threaded through the heap. It's almost as if we're copying the entire contents of the heap and just updating one piece at a time as we go from one to the other. That's the mathematical model, but of course, in reality, we're not going to make all those copies of the heap. We're just going to have one heap and we're going to change it as we go around. So that's the difference between the mathematical model and the way things execute, but math is a clear way of describing what is happening in a model. We can also look at static semantics for pointers. So the rule for new basically type checks E at some type T, and then new E will be a pointer to T. Dereference is similarly simple. If we have an expression E that is of type pointer to tau, then doing a dereference, *E, will give us the type tau. Finally, when we do assignment, the left-hand side of the assignment expression E1 has got to be of a pointer type, pointer to tau1. The right-hand side, we will type check to find out that it is of some type tau2, and then we'll check, is tau2 a subtype of tau1? Because it has to be in order to allow this assignment, right? We're using a tau2 where tau1 is expected. If that's true, then our overall assignment expression will be of type tau2 because remember, the assignment expression just returns whatever was on the right-hand side. Let's consider subtyping for pointers. It turns out there are no new subtyping rules to give. Why is that? Well, it turns out that a pointer type, tau star, is only a subtype of itself. We can use the reflexivity rule for pointers, but nothing else. So why can't int star be a subtype of long star, for example? You might think, okay, if we have an int star, then because int is a subtype of long, then int star could be a subtype of long star, and we can read something out of it, and it'll be fine, right? But it turns out that to cause problems. So let's look at this example. We have int star, an int pointer p, that's allocated as a new int. We have a long pointer q, which we assign to p. So note that because int star is not a subtype of long star, this will be an error in C and other languages. We want this to be an error because the next line is going to cause a big problem. Star q gets some long value. Okay? The problem is that if the type checker allows the second line, and of course in reality it does not, then the third line is writing a long value to a long pointer address, and so it's going to write 8 bytes. That's what we do when we write longs. But the allocated space was for an integer. There's only 4 bytes there. So we're going to write outside the allocation boundary, and this could cause memory corruption, including security vulnerabilities. Arrays are similar to pointers. An array type, tau array, is only a subtype of itself. It turns out that Java breaks this rule. It makes tau1 a subtype. It makes an array of tau1 a subtype of an array of tau2 if tau1 is a subtype of tau2. This is convenient because it allows us to treat arrays of subtypes, for example, an array of dogs, as if they were an array of animals. But it's not safe because if we have an array of animals that's really an array of dogs, we can assign lions into the array of dogs, and maybe the lions eat the dogs. Okay, I'm getting a little too anthropomorphic here. But the idea is that it can cause runtime exceptions when we write a supertype into an array. Java actually does this check. It will produce these runtime exceptions. And it just means that it's not checking as much statically as it could. The Java designers decided to do it anyway just because they felt the subtyping relationship would be useful, but we do pay a cost for that. That's part of the trade-off of language designs. Let's check our understanding about pointers.